All right, so welcome to our second lecture in this beginner's course on algebraic topology. Today's lecture is called Homeomorphism and the Group Structure of a Circle. And what we are going to do, first of all, is talk about homeomorphism, basic notion of equality between topological spaces. And then continuing on with what we did last time, talking about one-dimensional objects, we're going to talk about a very important property of the circle, namely its group structure. And the treatment that I'm going to give to this is somewhat novel and maybe unfamiliar to many of you. It was in fact unfamiliar to me until a few months ago. So it's a beautiful way of thinking about the group structure on a circle. All right, so I remind you from last time that we've been talking about two one-dimensional objects, or not the real line, rather the affine line and the circle. And I left us with the question of are these the same? And that, of course, implies another question. What does the same mean? So that's actually not so obvious what it means for two topological spaces to be the same. And it's a notion that only came into focus in the middle of the 19th century due to the work of Mobius, who we'll see in other contexts a little while later. So Mobius introduced this idea of what we're going to call homeomorphism. And so basically the definition is that two topological spaces, and let's make them rather general, so let's call them X and Y, are homeomorphic and that's written X with a sort of equality, squiggle equality, Y, precisely when there is a continuous map phi from X to Y, which has a continuous inverse. In other words, over here, maybe I'll say that the inverse is defined from Y to X. All right, this implies that this map phi is what we call a bijection. And that means it's one-to-one and onto. But it's a little bit stronger than that because we require that the inverse also be continuous. So let me give an example of which motivates this definition. Let's start with two topological spaces which are almost homeomorphic. Let's consider a line segment, okay, which is half open, half closed. Okay. So this endpoint is included and this endpoint is not included. And over here, we're going to take our familiar circle. All right, let's call that I, and this is S1. All right, so let's define a mapping between these, a bijection. So, well, we could give this some coordinates. Okay, so maybe we could start here. And we could end here, 0 to 1, and we could say that's a half, and that's a quarter, and that's 3/4, and so on. So that's just natural labeling on that interval. And over here, we could also make some coordinates. We could put 0, a quarter there, a half there, 3/4 there. And when we get back to here, we can sort of think of that as being also 1. All right, so now in terms of this labeling, we can just match up the points with the corresponding label. So we can send that point 0 there to that point 0. We can send 1/4 to that, 1/2 to half, 3/4 to 3/4, and then this point here back to there. That defines a mapping phi. And that mapping is continuous. It's continuous because if we move a point over here in a small continuous way, then the corresponding point over here moves also continuously. And it's 1-to-1, and it's onto. Notice this point here, this 1 point doesn't actually get sent here. There's actually no 1 point, but as we get closer to here, we're getting closer to this point here. So it's a perfect matching up. But this is a continuous bijection. But its inverse is not continuous. The inverse map, it just reverses things. So the inverse of 0 would be this point here. And so as we go continuously here, the inverse map would send points here to points here. But the trouble is, at this point here, if we go on this side, we go to points close to here. But if we go to points on this side of 0, then we're mapping to points over here. So if we just restrict ourselves to a little neighborhood there, it's not a continuous map, this inverse. Okay? So it's not continuous at the point 0. So this is not a homeomorphism, which is what we would expect, because we don't want the circle to be equal to an interval. Okay, so that's our notion of homeomorphism, and a notion of when two topological spaces are in some sense the same as far as algebraic topology is concerned. And now we can ask this question, are the line and the circle homeomorphic? So let's draw our line and our circle. And are these homeomorphic? Well, one of the key properties of this homeomorphism is that any property that we can discuss, which only depends on continuity, is going to be the same, or is going to be reflected in homeomorphic spaces. So if these two are homeomorphic, and they're not, but if they were, then any property that we could say about one of them would be valid about the other, as long as that property was only stated in terms of continuity. Okay, so to answer this, this first question, are they the same? They are not the same. But we need to give a reason. So why? So there's a property that this circle has which the line does not have. And this property is going to be very important for us as we carry on in more complicated situations. And here's the way we can think about this property. Suppose that we were a little one-dimensional worm on the line, and we started, say, at that point, call it the origin, and we went on a little walk. And suppose that as we went on a little walk, we trailed a string behind us. Okay, so we're walking, and we don't have to be always walking in the same direction. We can loop around a little bit, but we make a little walk. And when this means that I'm just walking along here, but I'm showing you what happens to the string. And move back over here, and then eventually we get back to where we started. So this is a closed walk. Closed walk with a piece of string that we stretch out behind us. Now, a property of this walk is that after we've finished and we're back to where we started, we can pull this string in. Just standing at the origin, we can pull the string, and the string will be pulled, tightened, until eventually all of the string is back at the origin. Okay, so all the string can be pulled back to the origin. That's a property of that particular space. But it's a property that's not shared with the circle. Certainly, if we make a little tour, we start, say, call that the origin. If we make a little tour that looks a little bit like this one, and we just stay around the origin and come back, then such a loop also has the same property. We can pull it tight, and it comes back to, the whole string comes back to the origin. But we are also in a position to take a longer, more complicated walk. So we could also take a walk that ultimately goes all the way around. And if we do that kind of walk, well, we've also returned to the origin, but now if we stretch the string, okay, so there's the actual space, and then after our walk, we stretch the string will be tight, but it will be caught in the space itself. The string, in this case, is caught. Well, caught by what? There's not an object out here. You can walk along the circle and make sure that the string is not snagged on any little trees or bushes. Okay, there are no objects to snag the string, but nevertheless the string is snagged in some fashion or another. The string in this case is caught by what? Well, by the space itself in some sense. So that's a property of the circle, which is purely in terms of continuity, which is not shared by a line. The existence of these paths which cannot be shrunk. So this is a distinguishing property. Now actually, a little bit of thinking shows that there are more than just this one possibility. There are other ways that the string could get snagged on the space. So once our little worm discovers this phenomena, the worm could then get his friends to take lots of little trips and explore what happens in different situations. And there are sort of more complicated things that can happen. For example, there's our circle again. And now we can imagine, let's go in this direction just to be different. So this time, okay, after tightening, we could end up with a string which not only goes around, but actually goes around twice. In other words, if you just send your friend out and go around twice and come back with a string and then you tighten it, then you observe that it's not only is it caught, but it's caught twice. So that's different from this kind of catching. There's then the possibility of going around n times. And in fact, we could go around either n times in the positive direction. Let's arbitrarily say that that's the positive direction, or n times in the negative direction. So there seems to be a different possible outcome, an outcome for every integer. So an integer, 0, 1, 2, either in that direction or in that direction. So for every one of these, we could associate a path that gets caught around the circle that many a number of times, where the positive ones correspond to going in this direction and the negative ones correspond to going in this direction. Okay, so what I want to do now is relate or give you some additional structure to the circle that allows us to talk a little bit about this phenomena and other phenomena in another way. And I'm going to introduce a very important aspect of the circle, which is its group structure. And this is a novel. This will be novel to you, because it was novel to me when I learned about it just a few months ago. And I have to explain where I learned it from. So I think the person who's sort of promoting this way of thinking is Franz Lemmermeyer. And I learned about it through a survey article written by S. Shirali in the Mathematical Gazette. In fact, in the Mathematical Gazette, which is volume 93 and number 526, which is March 2009. And there's a very pleasant article called Groups Associated with Conics that Mr. Shirali wrote, and he is actually, in fact, a high school teacher in India. So the level of high school teachers in India, at least some of them is very, very high. So I'm going to tell you about this. It was a revelation to me. It's the kind of elementary thing that one says, how could I not have known this years ago? You will all, of course, know that the circle has a group structure, although I know some of you do not know what a group is technically, so I'm going to introduce also the notion of a group at the same time as I introduce this structure. It's a very good first example of a group, I think. Okay, so here's our circle. And we're going to specify a point. Let's call that point O. And suppose we have 2 points, A and B, on the circle. I'm going to show you how to multiply those 2 points in a very simple and direct geometrical way. So how are we going to multiply those 2 points? Well, we're going to take a line through points A and B. And then we're going to take a line parallel to that line through the point O. All right, so these 2 lines are parallel. And we're going to define this point right here now, this new point, to be A times B. And I'll write times in a kind of a non-standard way, so you know this is not an ordinary multiplication of numbers. A times B. So suppose we had a third point. Let's put it here, for example. Then where would A times B times C be? Well, if we take A times B and we multiply it by C, what do we have to do? We have to draw a line like this. And then we have to draw a line through here, which is parallel to this one. Okay, so this is parallel to this. And now this point here would be A times B times C. But another thing that we could do, we could also take this product and try to write it in the other way. So what would happen if we formed BC first? Okay. So this might not work out completely correctly because this circle is only a hand-drawn circle, but okay. So there's BC. And so to calculate B times C, I would have to draw a line parallel to that one through O. Let's say like this. All right, so that's supposed to be parallel to this one. giving me that point there, which would be a B times C. And what about A times B times C? So if I wanted to calculate A times B times C, so that would be the product of this point and this point, I would get, well, I would draw the line through here, through A and B times C, and draw a line through O parallel to that. Okay, so maybe I'll give it a different symbol. It's that one. And then a line through O parallel to that. Okay, so, well, it looks like it's going to be the same. Okay, so that's, I'll put a squiggle beside that one as well. So I've just calculated that A times B times C, at least in this case, is equal to A times B times C. And you can check that that works not just for these 3 points, but for arbitrary points. Okay, so why is this happening? And let me say a little bit more about this multiplication. So a special case that I perhaps should mention is what happens when we have a point, let's say A, and we want to take A times A. What would be A times A? Well, so we have to draw a line through A and itself. Well, what would that mean? Well, if you imagine that A and, say, A prime are very, very close. Imagine the line through A and A prime, and then imagine moving A prime closer to and closer to A, then the natural thing to be looking at is the tangent. Okay? So what we really should do when we are multiplying A by itself is we should be looking at the tangent. And then drawing a line parallel to that one through O. And so there is A times A. Okay, so there's a number of properties of this multiplication. Okay, properties. What are they? Well, I suppose the first one is kind of obvious just from the way I've stated it, that if A and B are on the circle, so is A times B. We get another point on the circle, and that property is sometimes called closure. Just telling us that our multiplication is really well defined on our object, in this case a circle. The second property is that the point O acts as an identity. And what does that mean? Well, it means that if you take O times any other point in either order, either O times A or A times O, you get back the point A. Is that obvious? Yeah, so it's obvious. So if I multiplied O times A, what do I have to do? I have to take the line through O and A, and then draw the line through O parallel to that, which is the same line. So this is obvious, and this property is called existence of identity. Okay, and our third property is that for every point A rather, there is another point. Well, it might be the same. There is a point B, so that with A times B equals B times A, equaling our identity element. And that property we call existence of inverses. Is that obvious? Let's have a look at that one. Maybe here. So there's O. Let's choose A out here. Where is the inverse of A going to be? Well, I need to find another point. So when I multiply these two things, take the line through there and then translate it to O and find the other point of intersection, it'll be O itself. Now, how could that work? Well, the line over here that we get must end up being the tangent line, because that's the only line that meets the circle at O twice. And that means that the point B that we're interested in has to be sort of the reflection here. It has to be so that that is parallel to the tangent. So let's just make sure we understand that. If I multiply these 2 points, I draw that line, then I draw the line parallel to that through O, and ask where's the other point of intersection. Well, the other point of intersection is O itself. So this shows that A times B equals B times A equals O. So those are three properties of a group, and there's one more property of a group, which is usually the most interesting property. And it's either usually trivial or a little bit complicated. And it's the property that, what we've already established in that first example, that A times B times C equals A times B times C for any points A, B, and C. And that's called the associative law. Okay, the associative law here is not at all so trivial. Okay, it in fact turns out to be essentially a very important classical theorem. Does anybody know what the important classical theorem is that's really behind associativity here? All right, so I'll tell you, this is a consequence of almost surely the most famous theorem ever proven by a teenager. Does that give a clue what it is? This is a consequence of Pascal's theorem. Okay, Pascal, famous French mathematician, intellectual, who lived in the 17th century, 1600s. And when he was only 16 years old, he wrote a treatise in which the following theorem appears. It's a theorem in projective geometry, which was a theory that had been started roughly by Gergon a little bit before Pascal's time. But it actually has its roots back in antiquity. So before I'm going to explain Pascal's theorem, I'm going to just tell you a little bit about some basics of projective geometry. And I do this because the projective plane is going to end up being a very important object in algebraic topology also. Okay. So if you want to know more about projective geometry, on my YouTube in the Wild Trig series, I have 8 or 10 videos on projective geometry. Wild Trig in the 40s somewhere, I think. I'm not sure. I'm not sure where they are. But. Okay, so there are at least three theorems that all undergraduates should know in projective geometry. Okay? The first one is the earliest, goes back to Pappus, who was an Alexandrian mathematician of ancient Greece, and concerns two lines. There's two lines, and we have some points on these lines. Well, let's call them A1, A2, and A3. And on this line, B1, B2, and B3. And then Pappus observed that we could do the following. We could connect A1 with B2 and A2 with B1, get a line with a point of intersection, which we might call, say, X3, because it's 1, 2, and 3. And then we could also connect A2 with B3 and B2 with A3. A point there, which we'll call X1. And the other combination is A1 with B3 and A3 with B1. To get that point there, which we'll call X2. And now Pappus's theorem is that those 3 points, X1, X2, and X3, are all collinear. Okay. So X1, so what was X? Let me just write it down. X1 was A1, sorry, it was the meet of A2, B3 with A3, B2. Okay, so this is the way I like to write a line. That's the line joining those 2 points. That's a line joining those 2 points. And this product is the meet of those 2 lines. And X2 is A1, B3 meet A3, B1. And X3 is A1, B2 meet A2, B1. And the conclusion is that X1, X2, and X3 are collinear. That's one of the very famous theorems in mathematics, Pappus's theorem. Absolutely essential that undergraduates know this. Unfortunately, projective geometry has fallen a little bit by the wayside in modern times, but I think that's only temporary. Desargues, I said Gergon, I should have said Desargues, as the father of projective geometry. And his is the next theorem. Okay, Desargues' theorem. Okay, we have okay, we have 3 lines emanating from some point P. And then we have a triangle. Okay, I'm not going to, I'll just do it by hand here. So there's one triangle, which has its 3 vertices on these 3 lines. And then another triangle. Also the 3 vertices on the 3 lines. So we say these 2 triangles are perspective from this point P. These are 2 perspective triangles. Let's give them some names. A1, A2, A3, and B1, B2, and B3. So the triangle A1, A2, A3, and the triangle B1, B2, B3 are perspective from the point P. And what's the conclusion? Okay, so now what we do is we extend corresponding sides. So A1, A2, B1, B2, will extend those, and they meet there. A2, A3 will extend that, and B2, B3 will extend that, and they meet there. And then there's another pair of lines. This line here will extend it, and this line here will extend it, and we meet okay, down here somewhere. And if we did that very accurately, then we would find that these 3 points, this one here, this one here, and this one here, are also collinear. Okay, so let's give them some names. Let's call that one x1 in this case. A1, A2, so call that x3 and x2. So same kind of conclusion, x1, x2, and x3 are collinear. So that was Desargues around 1600s, early 1600s. They are the 2 most important theorems in projective geometry. They're the fundamental theorems in projective geometry. And it's projective geometry, meaning only a straight edge is required. There's no measurements. It's all just with lines. And then there wasn't really a major theorem discovered in the subject until Pappus's theorem was generalized by Pascal. So what's Pascal's theorem? Well, the simple way of saying it is that Pappus's theorem extends to the case when A1, A2, A3 and B1, B2, B3 all lie on a conic. Conic. So in some sense, two lines is a sort of a degenerate case of a conic. And so let's see if I can draw this. Okay, so A1, A2, A3, we'll put them there, and put B1, B2, and B3 there. And then just by hand, let's see, so A1 and B2 and A2, B1, so that gives us 1 point. That was called X3. And A2, B3, together with A3, B2, that was another point. We're calling that X1. And A1, B3 with A3, B1 gives us a third point, X2. And these 3 points are collinear. And it turns out that it doesn't, I put them here pleasantly so that I can compute these things pretty easily, but it doesn't matter where the points the A's and B's are. Right? So sometimes this is stated in terms of a hexagon, so sort of a hexagon inscribed in a conic. But that hexagon doesn't have to be convex, and it can be sort of self-intersecting. So the order of the points is irrelevant. Another important thing to say is that this is all in the context of projective geometry. And the projective plane, in this case, has to be thought of differently from the Euclidean plane. So this is in the context of the projective plane. And what that means is that, well, according to the geometer Desargues, this is to be thought of as the Euclidean plane plus some extra points at infinity, plus a line at infinity. A line at infinity. We need to add some ideal points or infinite points to ensure that in projective geometry any two lines meet, even parallel lines. Okay? So in projective geometry, parallel lines meet. So that a theorem like Pascal's theorem, in fact any of these theorems, also has an interpretation when two of these lines are parallel and meeting at infinity. And that's exactly the case that's required for the proof of the associativity of the group structure. We need to look at that very special case when we have parallel lines. So let's see if we can draw something like that. So this is sort of the back to the group structure now. And we're going to illustrate Pascal's theorem in the case where the hexagon has parallel sides. Okay, so what's the claim? So let's draw a hexagon with parallel sides. So that okay, there's 4 points, and okay, so let's draw a point down here. So these two are first parallel, and now we're going to do another point and sort of something from up here. So that's supposed to be parallel to this. And so if you draw a circle, and it's easy to draw those parallel, and it's easy to then draw something here, and that specifies the hexagon. So now the natural question is it true that this is parallel to this? Well, Pascal's theorem says that it is. That's a consequence of Pascal's theorem, because these intersection points now in this picture are all at infinity. Okay? So these two lines, the first ones, so these two lines here, they're meeting at some point at infinity because they're parallel. And these two lines, which is the second pair, they're meeting at another point at infinity. But the three intersections have to be collinear, and there's only one line at infinity. So if two of them are on the line at infinity, then the third one is also on the line at infinity. And that means that the third pair of edges, namely the ones that we're talking about here, these ones here and these ones here, they also meet at the line at infinity. So here's the line at infinity. And now if you go back to that picture of associativity that we were looking at, then the associativity of A times A1 times A2 times A3 equaling A1 times A2 times A3, it's exactly, the content is exactly this. That if we have two things which are parallel and another two things which are parallel, then the third pair is also parallel. So this is what associativity comes down to. So this group structure, this picture of the group structure on a circle is very attractive. It's completely geometrical, and it avoids any irrationalities. Often in courses in group theory, for example, you think of the circle as being the circle inside the complex plane. Then you can also define the group structure in terms of, in terms of the multiplication of the complex numbers. That's another way of doing it. So Z1 times Z2, you can use the complex structure of the complex plane to define multiplication. Or another way it's sometimes done is to use angles and to talk about e to the I theta 1 and e to the I theta 2, and the product of those being e to the I theta 1 plus theta 2. This picture here, however, involves the irrationalities. We're talking about i's, and there's sort of some pi's implicitly floating around. Well, this is a very pleasant geometrical construction. And it extends in interesting ways. So this group structure exists on any conic. In other words, not just the circle, but also the ellipse, or a parabola, or a hyperbola. And that's because Pascal's theorem, which is the essential underpinnings of the idea, Pascal's theorem works for an arbitrary conic. It's a projective theorem. It works for hyperbolas and ellipses. And so the group structure that we've defined here works just as well for parabolas and hyperbolas. All right, so now let me give you some problems to let you clarify this notion in your mind. So problem 4, show that with a rational parameterization of the circle that we talked about last time, 1 minus h squared over 1 plus h squared and 2h over 1 plus h squared, that e to the h1 times e to the h2, the product of those 2 points in these coordinates, is e to the h3, where h3 is equal to h1 plus h2 over 1 minus h1 times h2. For those of you who know your trig identities, that may ring a bell. And it gives a very concrete algebraic approach to this multiplication. And in fact, you could now check that the group operations are satisfied purely algebraically. That's a good exercise. I won't ask you to do it, but if you're unfamiliar with groups, that's a very good exercise to use this formula to prove associativity, to prove inverses, and so on. Problem 5 is to exhibit the group structure on a parabola. On the parabola, let's say y equals x squared, with our origin to be, our 0 point to be the usual origin, with parameterization alpha of x equals x squared. So a picture there. Now we're talking about this conic. You can multiply points using exactly the same prescription. And I want you to tell me what happens when you multiply 2 general points. What do you get concretely? And the problem 6 is the same kind of thing with now the third kind of conic, which is a hyperbola. So exhibit the group structure on the hyperbola. And the hyperbola will be y equals 1 over x, with the identity point being 0.11. And the parameterization, we could say beta of t equals t and 1 over t. So I want you to tell me, how does one multiply points on the hyperbola? So we're getting three different groups here. We've talked about the circle group, but there's also a parabola group, and there's a hyperbola group, and they're in fact different. And they're very important examples of commutative groups. These are all important commutative groups, very special and particularly pleasant groups. Commutative groups, they're the ones that satisfy the additional property that A times B equals B times A. So for those of you who have not had any group theory before, this is a great way of getting into the subject. Explicit groups, work it out, play around, understand these groups. They're really good examples. They're rather important examples, each one of them. All right, so next time we're going to say just a little bit more about one-dimensional objects, and then we're going to move on to two-dimensional objects, where of course things become much richer and more interesting. So I'll see you then.